you feel?
I'm okay. What did you see on there?
I don't know.
You don't know.
I don't know.
You have no contract to know about this one.
I'm sure he's okay. He's just got my.
This is not his job to you. Surrender. Okay. You will put your bed. No? I'm straight up.
Oh, wow, yeah.
This value provided by university?
Oh, cool. Looks like this fun, yeah.
Still open?
Yep. Oh.
Okay, so we wait and then let's start it. Let's start it. Just remind about the topic we talking about last time, and then we are going to keep continuing. So our purpose, we know that depend on different type of the potential, initial energy and the potential, we have the different type of orbital, either open or closed. Now we focus our interest on the closed orbit. What is condition such that we can find for given potential, right? Then we have this closed orbit. So we can focus on the power law. So that means the force proportional to R to the nth power. Then this potential is n plus 1, right? So that is the type of force we focus. If a different type, like exponential, that is other story. So for this story, I give you the supplement that is Bertrand theorem. So now to discuss this condition, first we start from because the condition circle is this minimum or extreme of this V prime. And if the second order derivative of A prime positive, that means give us the minimum. So we prove that for that one, we have the first condition for n to be larger than negative 3, right? But still we do not know, so even that is not, is any value is larger than -3 is okay or not, so that's the next one. Next step, we are going to start from the differential equation for the u, this formula, and then we are going to introduce or define some of function to replace some terms. One, the g function u is the relative term, and we introduce eta, which is the difference between u and u naught. U naught is the minimum, right? Minimum of V prime, which is circle. Then we also introduce the beta prime, which is 1 minus the first order derivative of g with respect to u at u naught. So when we introduce this, first we found the relation between beta square and n is this one. So the next one, we are going to see if we can find a allowed value for beta square, then we know for allowed value for n, right? So that is our continue discuss today. Now, when we introduce this, then we substitute into this equation. So this one is reduced to the equation, differential equation for eta. Then let's solve this one. So let's first consider the zeroth order. That means ignore this high order because eta is small, right? So in this case, we have this. And this one is simple, right? This is a simple harmonic solution. So we have the behavior of eta, which is, because we discussed, okay, I think here, since beta square is n plus 3, right? N should be larger than negative, so that should be larger than 0, right? Required. If n larger than -3, then this will be larger than 0. So we are looking for this case. If beta is larger than 0, so we have the eta solution is a sinusoidal, right? It's a sum of amplitude and let's say cosine beta theta. That is the solution. So you can see here the behavior of the u, or the difference of u with respect to the u naught, actually is a sinusoidal function oscillate with angle, right? So with this one, and that means if plot to understand the behavior of this, so now let's look at this one. So we have V prime, right? And then here, that is the prime minimum. Okay, then this one is R naught, right? R naught over U naught here. I mean, R is 1 over U, so that is that. Then we have, that means we have fluctuation is the energy difference. If at these zeros, we have the slightly perturbate, so system has a little bit of energy, so then this particle will move between, if it's a cloud, this is a turning point, right, between this. So that vibration, it changes R or change U naught, which is, if you can see, is something like this sinusoidal function, like this, right? And if you look the orbit, start from the initial, which is R naught, it's circle, right? Then if we have a fluctuation, this fluctuation is very small, so that kind of maybe like this. Something like this, okay, bigger, that is positive, not negative, or a kind of ellipse, right? So those are categorized the orbit of this. Now, but from here we still have no idea about the beta, how much it is. So now we go to jump to the third order. Third. Okay. Equation 1. So that means we are going, actually, if we have to add more, right? But we just check it up to here. Then we are going to solve this. To solve this one, we need some approximation method because direct to do that is not easy. So we first, from here, we know the eta has behavior sinusoidal function. So we can expand this eta in terms of the Fourier transform, right? Not Taylor expansion. So we do this way, and then we are going to substitute this to the equation. So okay. Okay. So we use the Fourier transform. Fourier series. So eta is a function of theta, which is 0th order is a constant. Relative constant means corresponds to the R naught, right? Circle, and plus the first order is fluctuation cosine the first order of theta, and then the second order A2 coefficient 2 beta theta, and third cosine 3 beta, right? That is a Fourier series. So now if we express eta in terms of this, then suppose we truncate this just up to the third order. Okay, that means truncate here. So then we have expression. Then what you need to do is substitute this into this formula. So I'm going to say this is equation 2. Then we are going to substitute the details, a sum of steps I gave you the material, right? I just give you some hints and then substitute 2 to 1. Since here we have, since we know this, so we can do the derivative. right? That is doable. And then we have eta square, eta cube. So all substitute into this will give you the final expression of this formula. Then we have the left-hand side. This part is beta square a naught minus 3a2 cosine 2 beta theta minus a3 cosine 3 beta theta. That is right-hand side. And the right-hand side is a1 square over 4 second order derivative of the J respect to u. This is a constant because this is only at u naught, right? And this is zeroth order at plus first order 2a1 a naught plus a1 a2 over 2 second order derivative cosine beta theta. And yes, use this clause here. The second order is a1 squared over 4 e squared j du squared u naught multiply cosine 2 beta theta. And the third order is a1 a2 2 e squared j du squared u naught plus a1 cube 24 j u cube u naught and multiply cosine 3 beta theta. So that is equation, you can say that is equation 3. Okay, since we explained in terms of the Fourier series of each given, this is the first order, zeroth order, first order, second order, right? So compare with those orders, we will have the coefficient both sides will be equal, right? So by comparing with this, we have the such formula. So the zeroth order, 0 order. The zeroth order in terms of the cosine beta theta, that is we have a naught equal to a1 square over 4 beta square p square j p square u naught. And say this is equation 4. And the first order, we have another equation is 2a1 a naught plus a1 a2 over 2 e squared j du squared u naught plus a1 cube 8 is this one. From that a1 8. Did I miss one, sir? Oh, yes, I missed one term. That is this one, plus here. Another term that I missed. That is a1 cube over 8 over 8 d cube j du. Okay, this term I missed. So here and come to here, we have d q j du cube u naught equal to 0. That is equation 5. Then the second order, we have a2 equal to a1 square over 12 beta square d square j du square u naught. And 6. And the third order, we have this one, we do not need it. Minus 1 over 8 beta square right? So this one is third order, is correspond to this one. We have 3 terms. And then we have only order 2 in the left hand side, order 2 is this one. And we have no order 1, so this one is 0. That is this. Okay, then we can substitute equation 4, 6. That's enough since we only need A naught, A1, right? A2, 6, right? So that this one into here. 2, equation 5. Equation 5, we do not have A3, right? So we do not do this one. Then, but the final result, the final solution of our equation is equal to not square plus 3 beta square qj du not equal to 0. Now reach down here, you see it becomes simple. Now the next job is try to find the derivative of g with respect to u, right? So we need to find these 2. Then we can solve the solution for beta square. That is our next job. So let me just remove this. I think we have here. Okay, I keep that one since we are going to come back. Now, what is G? Oh, G is here, right? So G is here. Let's rewrite G in terms of U, since G is partial V partial U, right? And so that is minus M or L square. Now partial V, I'm going to say partial V partial R partial U. Right? Just check. And this one is minus FR, right? And this one is minus 1 over U squared, if you remember. And then FR is here, right? Did I use negative? I think I need a negative. Negative KRN, but R is U1, so not negative K U minus N, right? Then N is here. N is here, so now it's minus K U minus, so that is a minus beta square plus 3, right? So you just substitute this, and then you find the J as function U. It is M K or L square U 1 minus beta square. That is the J. This J, so we can do the derivative respect to U, right? So that is so that is first. And second one, in this case, J U naught. Again, another information you can use is because J U naught equal to this one, right? So that means if from this formula is M K L square U naught 1 minus beta square, right? So this U cancel. Then we have MK, we have a condition MK L square of U beta of U minus beta square equal to 1. Equal to 1. This also very useful when we do the derivative. So when we do derivative, all the U will go to U equal to U naught. Then you can make factor, if we have this factor just equal to 1. Right, so these 2 equations, by use these 2 equations, and then we can do this derivative. Now I'm going to give you the result. So finally, we substitute into here, so we have final equation for the beta. Just, so finally, that is equation 8 is reduced to, okay, 1 minus beta square beta to the fourth power, 4 minus beta square equal to 0. That is equation 9. You have a question?
No.
Oh, okay. Yeah, definitely. Yeah. Okay, so now this is a final solution, very straightforward for the beta square. Then the beta square has several possible equal to 1, right? First one. If beta equal to 1, so n equal to, you see here, n equal to beta square minus 3, right? That's equal to 1 minus 3 is minus 2. And which one? The fourth is minus k over r minus 2. That is an inverse square, like Coulomb potential, Coulomb force over gravitational force. That is in nature a very powerful, right? So that is that means yes, we know for Coulomb potential over force over the gravitational force, we have this closed orbit like Earth move around the sun and the moon move around Earth, and all this will be familiar, right? So yes, that is the case. N equal to minus 2. Second one, this one. Beta square equal to 2. Okay, beta square equal to 2, and then let's see, n is beta square minus 3, that is 2 minus 3. That's 4, not 2. That is for 1. So which force? Hooke force, right? So force F is minus K R, okay, 1. So that is nothing but just say. You don't need the red one. So that is. And that case we also know is a simple harmonic oscillator, yes, either linear but always limit over. We have 2 vibration X and Y and move from the circle over the ellipse over like Lisa Jones figures, all are close, right? But another one, 0. 0, we know n is beta square minus 3, that is minus 3. That means n is, because we had the solution, conclusion n must be larger than minus 3, that is close. But equal to 3, the fourth cannot have the stable one, right? Fourth is minus k over, so that is open or unstable orbit. Okay, so now we put, and of course the details, some of the intermediate step about this math, I think I give you a film, you can do that, or you can refer this the supplement I gave you. So that is the general theory we discussed for this central force problem. Our goal is try to see what type of orbit it will give and for given energy and also different type of potential or force. Now we discuss, it is if it is possible to give this a closed orbit, the force for the power law, the force either this one or this one, only 2, right? So that is the conclusion. Now we go to next step. We just analyze qualitatively which type of force or can give this a stable or closed orbit. Now we are going to calculate or describe what is the orbit. We have not yet solved, right? So now next question is, this is our initial question. Before we doing that, we just analyze. Now we got come to here, right? So now we are going to answer this question to give the detailed formula, and we will focus on this one. This one, I mean, you can also follow the same idea. You can do that, but let's read this one. Let's say focus on n equal to minus 2. That is inverse square law. Let's just do this. And that is nothing but we call Kepler, because Kepler focuses on the planet, right? And our universe, so the stars, those are all follow this, the gravitational force. That is the Kepler problem. Where it comes from, that is inverse square law of force. For this type, of course, does not mean only the gravitational, but also the Coulomb force also follow, right? So now let's discuss this case. All right, so now we are going to focus on this, how to get this, the orbital, the r as a function of theta, the details, right? So how to solve this? Remember at the beginning we have this, to solve this orbital equation, we have two types, differential equation and integral equation, right? So it's a big money differential equation for orbit. The first one is for orbit is this one, if you remember, L squared over R squared d theta L over m r squared dr squared dr d theta minus L squared over m r cubed equal to fr, or we use u, right? D squared u, which that one. D theta squared plus u equal to negative m L squared plus u plus u, right? Is this this one. Right, this is a differential equation for the orbital. We have also another one, the integral equation for orbit, which from this conservation law, right? So another equation, so which one you are going to use, it really depends. For example, when we discuss this, use differential equations better. Now, when we obtain this one, use integral. Okay, so now integral, you remember theta equal to theta naught minus, since we start from this conservation angular momentum, we use that formula to obtain this. In terms of u, since that is a little simple expression of this integral, plus 2m ku L squared minus u squared. Here, I already, the potential, this is potential, right? I already subject the potential here. As we discuss this one. So we discuss this one. This case, force is minus k r to the minus over minus k u squared, right? And the potential is be minus k r to the first over minus k u, right? So here, this is u, remember? Then, of course, they have coefficient 2ms L squared. Yeah, in the parentheses, e plus u plus v, remember? Yeah. So that is direct here. Okay. We can rewrite it in this way. This is a definite integral from this theta naught, which corresponds with t naught, which angle it is, and go to n theta is the path. But for this definite integral, we can also replace by indefinite. Let me write down this, and I'm going to expand. If you agree, I don't need to expand it. If you're not, and the denominator same thing. K u over u squared plus and minus u squared here. So any integral from this definite go to indefinite. Infinite is always plus some constant, right? And this constant is determined by what is the initial condition. So when they replace this by this, here replace by this, and this constant plus this and plus this one, I'm going to design a theta prime, another theta. Right? So that does not change our result. We just want to have the formula, but the formula, those theta prime just depend on arbitrary angle which you are going to select it. Make this more arbitrary than this one, right? That makes sense? So, so we are going to, let me see, if this is the equation I'm going to re-equip, so that story is finished, right? So now let's start here. 1. Okay, now I can erase those. All right, so to solve this one, if you look, since it's u, this is a constant, first order u, second order u. And we have a general or a special integral which we can have this solution, right? So now let's see. Because, you remember, in general, if you have this definite integral with alpha is constant, beta is another constant, x plus gamma x squared. This one, as the result, let's give you the result. It is 1 over square root minus gamma arc cosine, and inside it's negative beta plus 2 gamma x over q. And here q is beta squared minus 4 alpha gamma. So you see this integral doable, right? Since it is really just this one. The only difference we are going to find what is alpha in this case. Alpha is that right? That is the first term. So alpha is 2me over L squared, right? In our case. 2me over L squared. And the beta is that one, the first order. 2mk over L squared, right? Yes. And gamma is minus 1, right? Okay, and then I have also q. So now let's substitute q here. I think I just use this space here. Q is beta squared is this square 2mk over L square minus 4 multiply alpha is just 2me over L square. And gamma is minus 1, right? So that together I take this one outside, 2mk over L squared outside. So we have this term inside. This minus became plus, right? So then this is a 1, square. This is a 1, and then this is a plus. I have a divided k, right? Because this is a square, we have a k square. And e is here, we have this is a 2m comma, and we have another term, so let me do L squared over mk squared. That is q. Okay, so very easy, we already have the solution, we just substitute those into this result. So finally, you will have that theta equal to theta prime minus that integral, right? Minus this integral, and I just directly put it here. Minus, that is 1 over square root here, right? Minus 1, gamma is minus 1, right? And arc cosine inside negative. Beta is here, right? 2mk over L squared. Gamma is minus 2x, sorry, theta, right? Now x is u, sorry. Because this is u, right? X in our case u. Okay, so that is, and the denominator is this square root q, so q is here, right? Square root, then we have this, this 2mk over L squared and square root inside 1 plus 2e L squared over mk squared. Okay. This we do not vary because minus become plus, so that square root 1 is 1, right? So that is now continuous theta prime minus this one arc cosine, and we organize this one, so I give you this which is L square, since we have divided this one both sides, so we have, and this is a 1, but then they come to here, right? So I have a minus plus, so I put this one as first. So that is L square MKU minus 1, right? This cancel. And denominator, 1 plus 2E L square MK square. That's all. Very good. Right, so now it's a function theta, then theta minus theta prime is arc cosine L or MKU minus 1 and square and plus 2E L square MK square. So we can get this cosine, right? Since we know the theta, then the cosine as a cosine theta, this function. Then we have a cosine. I think I have a minus sign here, right? This minus here. So here, that means cosine minus theta prime. We know cosine negative angle is equal to positive, right? So that is the first. And then that's equal to this one. That is immediately we have this. Equal to L square or M K. Now, U is 1 over R, right? So here 1 over R minus 1 plus. Okay, then plus 2E L square or MK square. That is. Now, of course, this is a cosine theta. Now we are going to find R, right? So now let's first move the R. 1 over R is, you just manipulate this formula, so we have the final result from 1 over R, since we have L square, so that is coefficient. 1 over R, and then inside 1 plus square root, 1 plus 2E L square or MK square cosine theta minus 1. Right, we just multiply cosine this to here, so that is this term. And then this one, right? So then you move this one to the left side, but you have a coefficient here, so that is this. Okay, so that we obtained this equation number 3. This is 1 over R, proportional to the cosine, but now we are going to find R, right? That is our question. So now we got it. R as a function theta, now let's take inverse, right? So now the denominator is L square over MK. Is this one, just reverse. And this go to denominator 1 plus square root 1 plus 2 L square MK square cosine. Very good. So we obtained the orbital, but R as a function of theta, in case if this n equal to 2, right? That is inverse square law. So this is a solution, and the answer this one. Now we can discuss. This formula gives us exactly relation between R and theta. So we can plot, for given R, given theta, we can plot R, and then we can have the orbit, right? So now we are going to discuss this, what this means, what kind of orbit it gives us. Before doing that, I can also give us the byproduct. So you can see here, we obtain this one, and if we really want to find theta as a function of time and R as a function of time, it is doable now. How to do it? Okay, so because this one we can get from the theta dot. Remember this conservation of this angular momentum. We have this d theta equal to L dt, right? Remember this, and you just substitute here because this is a function theta. Let me just write the details here. So since we have r as a function of theta, so in principle we can solve, right? You just substitute this one into here, and you do the integral in left hand side, do the integral right hand side time. So in principle you can get this one. And when you have this, so how to get this one? This one is from the r, if you remember r, we have also the integral at the beginning of the do this, actually just from, r dot, if you remember r dot, I think I didn't write down here, but do you remember r dot is from energy conservation. Square root of, I need the square root of, because this is energy is half of mr dot square plus L square over 2mr square minus, right, k r, 1 over r, right? That is this. Just from here, and we can got this one. So, okay, let's just write down here. So from here, we can get r dot, and then because this one is, r dot is dr dt, right? Then you can have something with a function of r, theta dr, and then something with dt, something like this. You will find that something like this. But or, let me see, dr, yeah, r is to give us theta dr. Maybe you can do this way. Add dr d theta. So here, you can get the dr d theta from here to the derivative, sub to here. So this left hand side is an integral with respect to theta. The right hand side is with respect to time. So in principle you can do, but I do not want to spend time here. So that is in principle we can do. Now we want to discuss this one. To discuss this, the behavior of this, what kind of orbit. So now we are going to discuss this. Okay. First, let's, you see there's a lot of these the numbers here, right? So we want to make this easier to see the curve or curvature of orbital of this. We just introduce this E, and we know that E is eccentricity, so that is not here, we have this one, right? So we take that as a constant, 1 plus 2E L square over mk square, that is good, right? So that is eccentricity of the orbit. And we are going to discuss this one in more details. Sorry, not orbit. It's a conic section, which is conic section mathematically. It gives us what kind of orbit. So we introduce this, and the second one, capital P. Here, this numerator we also introduce a constant. So P is L square over mk. Then R, it becomes simple. So R is P, numerator is P, right? Denominator is 1 plus E cosine theta minus theta prime. See here, that became very clear. It is only function of the E, of course, E is constant, depending on initial angular momentum and initial energy. Different initial energy, it will control the curvature of this. So later we are going to discuss. All right. So now, let's see. This is the first we define, right? So second, now we consider the relation or what control the orbit or relation between E. Energy, for given energy, remember we have the, now we already have the potential. We prime. So now, depending on the initial energy, with the positive equal to 0 or negative, we will know there's open orbit or closed orbit. So that we are going to find the energy. Now you see, when give energy, this is control, right? And this will control R theta. So now let's discuss this relation between those. All right, the first one, case 1, energy is positive. So energy positive, look at what is E. If this positive is larger than 1, right? Right, because this is a 1 plus some positive term. So we have larger than 1. Okay, now let's look at the R. R is P plus 1 plus, let me write down here, cosine theta minus theta prime. Formula doesn't change, but if you remember, you keep in mind this is larger than 1. Now let's look at the curve. V prime, and we already know the V prime is like this. Now the energy is here, right? So what kind of, we already discussed this, so we know there is a one turning point, R1, or let me say, in this case, I'm going to say R min. The smallest R, right? Lower than that, smaller than that, we cannot go, that is forbidden area. R min. So from here, can we get the R minimum? Mathematically, when the cosine theta minus theta prime is 1, right? Because the larger the denominator, the smaller r, right? So the larger one is this take 1. So the R minimum immediately can obtain that P1 plus E. Okay, then what is R maximum? When cosine is from this angle from -1 to +1, right? So when the E multiplies some negative term such that this one equal to 1, then the 1 minus 1 go to infinity. That is what happened, right? So what kind of orbit? I don't have space, I have no space there, so nothing comes here. You see now, we discussed qualitatively before, but analyze this. Now we have the orbit, so we want to revisit this topic. Now we have exact expression for the orbit. Okay. So the orbit, what is orbit? See here, we introduce this one, this eccentricity of the conic section. So now, what does it mean? Let's first look at our conic section. That's a conic, right? Conic section when epsilon E equal larger than 1 is this transaction. And then what we have is a transact here, right? That is hyperbola. Let me use black. That is when we have the transactional surface just parallel to this conic axis, we have two curves, a hyperbola. And we discussed before, yes, this hyperbola. So hyperbola, which is open circle, open orbit, right? And the hyperbola that is graphically, so now the formula mathematically, we also know that is this one, right? Mathematically, to express the curvature of the curve that the give this hyperbola is this one, right? Sorry, minus. Plus is ellipse. Or there are two cases. Or x squared get b squared minus y squared a squared. So this one depends on a. If a is larger than b, then the curvature is either west, east, or top and down. Okay, so you see, we have a more detailed expression to this correct orbit. Either you use this formula, or if you plot this one, you can write a small program you mathematics. Whatever it is, you can input this one, change the theta, you will see you plot is like this, right? Like this, right? Okay. So there's a first case 1. Now case 2. Just equal to 0. If n is equal to 0, so we need see the condition, right? So the relation. If n is positive, e is larger than 1, then we have r. Now if n is equal to 0, this is equal to 1, right? Because this term is 0. So that equal to 1. Okay, then r p over 1 plus cosine theta minus theta prime, right? No e here. This e is equal to 1. So that is the case. Then what happened? We also look this curve, if you remember. That corresponds to energy equal to 1 here, equal to 0 here. And we still have this one turning point, right? Only one turning point. So now here we have r minimum is either from here, when cosine theta minus theta prime is equal to 1, right? What is R maximum? Again, when cosine minus theta minus theta prime is equal to negative 1, that is pi, right? That is also go to infinite. So we have that the picture is still open, and now the orbit, right? So this is then we look the orbit. In this case, this e equal to 1. So from this conic section here, when e equal to 1 is correspond to this truncation. So we have the curvature is like here. Something like this. This is a parabola. Relatively, we can see this, visualize this curvature is like this because we can use this E truncate in this conic section. Then the formula, mathematically, we also have the formula to describe the parabola curve. I just keep here. So parabola curve is y squared equal to whatever it is called x, right? Yes, that's all we can see, and that is like this. Parabola. Then go to infinite is parallel. This go to infinite, go to this asymptotic behavior. Okay? So that is different. Okay. Second one. Now let's consider this case 3. Energy is negative, but the negative still larger than the minimum, higher than minimum. So that let's consider this case. In this case, how about this eccentricity here? If this is negative, that means 1 minus something, so that be smaller than 1. Then the R, again, in this case, we still keep, since E is not equal to 1, right? So we still keep it. But now we know this is less than 1. So with this, now let's look this R, in this case, what is R maximum, R minimum? R minimum is when this equal to 1, right, cosine. So that is P over 1 plus E. R maximum minus 1, right? So you see here, these two cases, R maximum go to infinite. That means this is open. This is open only. Here we have a limit because maximum and minimum has a limit, finite value. So the work is obviously closed. So now the orbit, in this case, if we use this conic section, okay. So that is not parallel, it's like sum of order, sum of this one is ED. This is a close orbit. And mathematical formulas in this case, we also have this formula to plot okay. And that is here. What is A and B? There's a major axis and the minor axis. This is A. And minus A, but even minus B. So we have this one. And you can see here, which is this one is R minimum, and this one's R maximum. Okay, last one is the last case. When energy is just equal to the minimum, right? So case 4. So, what is value when energy equal to minimum? This this one, I want you to focus, but the minimum, the weight minimum is let's see, there's a d v prime d r equal to 0, right? From this case, we get r naught because this is circle, right? V1. So that is V minimum, right? V prime minimum. That is E here. And that is R naught here, right? Circle. So to determine this R circle by doing this one, so I just gave a result since we know this. And I'll give you this one. V prime is V plus, remember this? And V is minus K over R, right? So dV prime dr equal to 0. I just gave you, you can do yourself. R naught is equal to L squared over mk. See, it's nothing but P. Interesting, right? So this P come from, it's when we do the circle, that is just the radius. You just do it, I think. And then, okay, so that is this, then this one, then you will see the E prime, V prime, minimum. Because it's, then we can immediately obtain the V prime minimum. You just sub this into here. You can get this V prime minimum is minus m k squared over 4L squared. Then now you can see here, if E, that is this term, right? They cancel. So energy, if energy equal to V prime minimum, then that means 2E L squared over mk squared is equal to minus what, right? Because it's minus. Then E equal to 0. That is how we get this. Other case we can analyze the E, but this case we need no. So now you can, if E equal to 0, then R is P1 plus 0, right? Because the cosine here, this is 0. So that makes sense because R is constant. Since it's a circle, right? See, interesting, right? Just from this formula, depend on E, and E depend on energy, then we have different type. Okay, so I think I can erase this part. I keep that one. Now, this is a circle we're familiar with this. So for this, if we can see the orbit, how to get the orbit from this conic transection or conic section, that is also when E equal to 0 means what? Means we just truncate the surface or plane is just parallel to this bottom or top. So you will have, yes, that is circle. And it's a close orbit. Okay, and mathematically we also know that that is a squared plus y a squared equal to 1, that a is nothing but a radius. Okay, so let's see at the time. So now we have discussed obtained the orbit, and then we can discuss the relation between energy and energy control the E, and E gave the different type of orbits. Now let's focus on ellipse or circle, just close orbit. Since this R can have any type, right? Either open and close, depending on the energy. Now we do the further discussion about this orbit, which is follow the closed orbit or ellipse. Ellipse special case is circle, right? So now we discuss the first issue is this one, right? Did I make a second? So discuss case 1, I think, and then now discuss second one is focus. I forgot. This has an E, I do not. Focus on E. That is, energy is negative, and E is between 0 and 1, right? If equal to 1 is parabolic, equal to 0 is circle. So now if we discuss this, let's do, we write this formula, this orbit. Now first, the term knowledge, we have give some of terminology. Since whatever is, if you're interested in the astronomy or do some homework, the problem say that's abscess, what does means? That is correspond to theta equal to theta minus or equal to theta prime, so that is then they equal to 0, right? So in that case, then they go to the R minimum case. R minimum is this one, right? It's P1 plus E. Then we call this point is abscess. Then theta minus theta prime is plus minus pi. That gives R maximum, which is P minus over 1 minus E, right? So we call this is per center. Okay, from now on, let's instead of R minimum use R1, and this is a F center, and which we use R2. Okay, that is here, right? This R minimum, R maximum, we use R1, R2. That, and then we can also, at any point, any turning point, turning point, we have also the term knowledge. We call this epsilon, either R1 or R2. So that we call epsilon. Then the orbit, okay, so if in terms of orbit about sun, because this is developed historically, so they have this other name about sun. We called R minimum is perihelion, and R maximum that when Earth close to the sun, we call this Earth at this perihelion position, or aphelion. Aphelion. Okay. If the orbit is like moon around Earth, right? Then another name for the R minimum, they call this is upper G. And for R maximum, they call this parity and upper G. Okay, so that's terminology, and with those terminology we can go to the next discussion about the relation between the orbit and the other parameter which we are going to introduce. Okay, so we introduce the semi-major axis now. So this is A. You see the A here. Okay. A is from this is X. This is Y and this is B. From 0 to this place B. So we introduce this A is semi major axis. So we are going to now, since mathematics have this numbers A, B, so we want to find the relation between A and R minimum. Now let's use minimum or R1, R maximum. So now we are going to find the relation between A, R minimum, R maximum, and also energy. You will see here, this A, whether the orbit shape is A is longer or shorter depending on energy here. Then they definitely also R minimum, R maximum, right? So now we are going to find the relation. Here, okay. All right. Since we need to use the energy here, so I'm going to rewrite this one. Minimum is this one, right? 1 plus E. But remember P is here, right? So now I'm going to is L square over MK 1 over and our maximum is P over 1 minus E is L square over MK 1 minus E. Let's use this one. So now C. This is A, right? 2A together is R minimum plus R maximum. Right? So 2A, half A is a half measure, so the total is 2A is a major axis. That's the R minimum plus R maximum, right? So from here, since we can substitute R minimum as maximum into this formula, we can find A relation with this, and then you will see relation with E. So now I'm going to substitute, I think that is simple. Now I'm going to give you L squared over MK and 2 over 1 minus E squared. And then now E is here, right? So I substitute E into this formula. You will see here, okay, let me write down the intermediate step. MK 2 over 1 minus E is 1 plus 2E L squared over MK squared. And then you cancel each other, you will find very simple. The A is minus K over E. So now let me summarize. So here we have the relation A is negative of K over 2E. This relation is very important. That means A depends on energy. So the initial energy, even though the energy is negative, but it can change from the minimum. We plug minimum to any value before, below the 0, right? So that means A will change. Then you can see here, E small and small. Of course, energy is negative. So you will see here, A small is close to 0, right? So A will go to infinite if energy close to 0. And that is parabola. That makes sense. Right? So you can see here, for the ellipse here, with A small, if A just equal to the A naught, then that is R naught, then that the Rm, minimum R must be the same, that is circle. That is in case is that value when E, I erase, right? When E equal to, then we have A equal to R naught, right? We can prove very easily, right? Then the E equal to close to 0, A will go to infinite, then the orbit will open. So you can see we introduce another, this parameter and this parameter are also controlled by energy, which control the shape. So that gives the shape of E. And this shape, again, depends on energy, right? That is this one. Then when we have this A, introduce A. So now, let me see relation to, okay, so now we can discuss what's until now. Let's see the relation between, since A is controlled by E implicitly, right, or indirectly, A, R, minimum, R, maximum, and R. We have also this relation. So here, you will see this, see here. Okay, because E square is 1. E square is this one, right? L square over 2 M K square. M K square. Then E is here, right? So we replace that by the 2K, because minus sign over 2E L square over MK square. Sorry, this A, sorry. Sorry. Then the E is just minus K over 2A, right? K L square over K square. And then you can see this one is 1 minus L square over A MK. And L square over MK is P, 1 minus the P is P. P over A, right? Then you just do this, you will find A multiply 1 minus E squared is P. So we have this relation here, and with this relation you will find that the R is P over 1 plus E cosine theta minus theta prime. Then this P is from A 1 minus E squared over 1 plus E cosine theta minus theta prime. So that in terms of E and A, not P. That is another formula for R, which we are going to use later. Then this R minimum, or called R1, is P over 1 plus E, right? Then P is here. So I substitute P here, then you can see very easily that A 1 minus E squared over 1 plus E, so that is A 1 minus E, right? Similarly, our maximum, usually we say R2, which is P over 1 minus E. Since P is A over multiplied 1 minus E squared, 1 minus E, so that is A 1 plus E. This is another. And the textbook gave us the relation that, so that you can see that curve is very easy to understand. So we can look this relation between the R1, R2, and E. So now, if this E from 1, okay, that is E, right? From 0 to 1, that is corresponds to limit. And R1, let's see, R2, okay. R2 as A and R1 as A here. So you can see when the E equal to 0, R1, R2 equal to A, right? So R over A is 1. That is R over A. Okay. R over A. This vertical axis, and the horizontal is E. So then you can see R1 with E increase, they decrease here, right? So that is 1 minus E. Then from 1 minus E from 0 to E, so that is over here. And then the R2 is 1 plus E, right? So R over A is 1, but when E increase go to 2, right? And you can see between, so this gives a different type of this this object. So here, if I say this is a when we have this is A. When this appear, right? So that is R1 equal to R2 A, and then this that is E equal to 0. Then if I increase E, you have an ellipse. You have an ellipse like this. Because A is a point 75, and if you have a more narrow, increase, right, 29. Then open with infinite when E go to 1, you will have this parabola. So you can see here the A is, of course, in this case, this is let me see. E is also depend on A. I think I will not write A here. Maybe that is R now. It's better. So that is. Sorry. Okay. I think almost discuss this. The next job we are going to discuss the velocity and the what is period. How to obtain period. One cycle. How long it is. Then we are going to introduce this time. The period is not easy to obtain because the integral is complicated. So we can only do some special case. Then we also introduce another formula for the radial object R as a function. Introduce another angle, which make this discussion. The formula is easier. So next week, I hope we can finish the chapter 3. I try to focus on some important one. Is I'm going to discuss the velocity and this period. Then I'm going to discuss the scattering. Talk about some of the energy positive. We have this parabolic or hyperbolic. So that associated with the scattering. So we want to also discuss another different way, right? This is a closed orbit and open orbit. That is my plan. I'm going to assign homework next Thursday. When hopefully in that time we almost cover the chapter 3. Okay.
그러죠.
See you.
못하냐고 내가 가는 사람인데.